Hello, my name is Richard. Welcome back once again to my channel. The last time we started with chemical kinetics and we kind of did the introduction to it, talking about rates of reaction and what affects those rates of reaction. Today, we are going into details on how to calculate the rate of these reaction. Now, as I said earlier, the rate of a reaction is just how much reactants are consumed over time, or how much products are also consumed over time. So let's consider this a generic reaction. If we have this generic reaction 2A plus B giving us C, right off the bat we can say that 2 moles of A combine with 1 mole of B to form 1 mole of C. But for us to write the rate of reaction as to how this reaction proceed, first we need to know the rate at which each reactant is consumed, right? So the rate at which each reactant is consumed is basically the concentration of the reactants in mole per decimeter cube or in mole per liter over the time taken. So the rate with respect to A, so I could say the rate, which is rate with respect to A, is going to be the concentration of A, or let's say the change in concentration of A over change in time T. With respect to C, is also going to be change in concentration of B divided by change in time T. Same thing applies to C over here. Now we could say each rate is also change in the concentration of B divided by change in concentration, change in time. But if we look at this carefully, what we could say here is that it just tells us the change in concentration, right, of the various reactants and then the various products. But looking at this equation specifically, we can say that the reactants are not being consumed at an equal rate, because for every 1 mole of B that we do consume, we consume 2 moles of A. So over there the rate is off, or the balance is off. So if we try to find the overall or the rate of this reaction by just comparing the concentration like that, it wouldn't work out. So the only way we could do with that is for us to make sure that all of these are having the same rate. In other words, for us to determine the rate of that reaction, we should divide it by their respective stoichiometric coefficients, and the stoichiometric coefficient is the 2 over here. Over here would be 1, and over here would be also 1, but we do not write the 1. So to write the rate of these, the rate of the reaction with respect to each of these entities or products and reactants over here, we are going to have something like, with respect to A over here, we're going to have 2, right? So by so doing, let's consider another generic reaction. If we consider this generic reaction, AA, can I see? So let's consider this reaction. AA combines with B to form C, and then D over here. In this reaction, if we are said, or if we are tasked to calculate the rate of this reaction, and once again, let me clarify it, rate is either how fast the reactants are being consumed. Once again, the rate of a reaction is determined by how fast the reactants are being consumed, right? Or how fast the products are being produced. So it's either reactant or product. It is never both. It's either reactants or product. So if we are said to determine the rate of this reaction, or is going to be something like the rate, right, of say, and then if you do it for a generic reaction like this, which is irreversible, the rate of the forward reaction going forward like this is going to be how much of the reactant we are using. So that is going to be the change in concentration of A. So the rate is going to be the change in concentration of A, right, divided by its specific A change in T over here. This is with respect to A. If we want to do it with respect to B, it's going to be a similar thing, the change in concentration of B divided by the stoichiometric coefficient B and then the change in the time T. Now it will work for either you want to do it in the reverse way, as that would also imply the change in concentration of C divided by C change in T, and the same thing will go for D2. D changing D over here. Now once that you have this situated, how do you write the rate expression for it, right? So for you to write the rate expression for it, or how the rate of the reaction is occurring, you could go with any one of these to determine how the rate of the reaction is getting. If you do it for A, you will get the same answer as you do it for A, B, C, or D. They will all result the same answer. But that gives us, or that leads us into what we call the rate expression or rate law. The rate law. Now, the rate law, as we all know it, compares the rate or the consumption of reactants, or the producing of these products, right, in orders of magnitude, or as in the orders in which they are being produced. So still considering a generic reaction, pause it. Yeah, we're going to do the rate. So if you are going to do the rate with respect to the reactants, you should put a negative sign in front of them, right? The reason why you put a negative sign in front of them is because even if you think about it logically, they are being consumed, they are being reduced, they are being taken away, or they are being used. So it is negative if you are taking them away, or you are using them, or they are being consumed. For the product, it's always positive in front of them because they are being produced, they are being created, they are being born into existence. So they are adding onto whatever is there. But for the rate law, still considering this generic reaction over here, we can go ahead and then say that our rate, the rate law or the rate expression, is equivalent, or is directly proportional. This is how I write a proportionality sign. It's proportional to the concentration of A to some order, and then the concentration of B to some order, right? Now we can have all the way going if we have more reactants forming. So if I'm changing the sign of proportionality to make it an equal sign, the rate is going to be K. Then the K over here will become the rate constant, right? X dot dy over here, where the K is equals to the rate constant. X, Y, Z, if we have more reactants, are the order of reactions. Now, the order of reactions are determined only experimentally. These are not constant values that are always there, and they might change from reaction to reaction. What these orders of reaction tells us is that on what magnitude or on what order of perception is that particular product being consumed or being produced. These are the rate order, and they are determined only experimentally. Under no circumstances are you going to go on the MCAT and these orders over here are already given, or they are just there what the MCAT usually does is they give you a set of experimental data in conducting a said experiment. Now they would give you the concentrations of these things under different conditions, and you are supposed to hold some conditions constant, and that would allow you to find the order of magnitude for the other conditions that changes in the reaction. So from here, if we are going to calculate the rate, there are 4 things you should know. There are 4 mistakes or tricks that students usually fall for when they are calculating rate constant of a reaction. Now, the mistakes that you might face when calculating, so let me just put it here, tricks in calculating rate. So the first trick over here is that the stoichiometry coefficient, this stoichiometry coefficient over here, they are almost always never the rate law over here. So let's take this generic reaction for instance. If I'm said to find the rate expression or the rate law expression for this reaction, I could go ahead and do it in something like this. The magnitude of A dot X and then the magnitude of B over here dot Y. But this X over here is never these two. It's never it, or this Y over here is never the one that is in front over here. Now there are some instances where it might be these two, and there are only 2 instances where they might be so the first trick is that the stoichiometry coefficient is never one more green. The stoichiometry coefficient is not the same as the order of the reaction. Right, that is the first mistake you might encounter, and there are 2 instances where this might not hold, that the stoichiometry coefficient might be the same as the order of reaction. The first one is that when the rate determining step is given and the reaction is the first one is if the reaction pathway or the mechanism of the reaction is a 1-step reaction, and that 1-step reaction reflects the entire, it is just the actual reflection of the entire chemical process. So if you have the mechanism, the reaction pathway, which is the mechanism of the reaction, the last time that we did the mechanism pathway, that we drew the graph over here. If we have like the mechanism pathway, where over here it gives us our activation energy, right? And then from here to here is the change in Gibbs free energy, and over here we have the reactants, and over here we have the products, right? If this reaction pathway is given and it's a 1-step reaction, meaning there are no intermediate form in the reaction whatsoever, then the balance equation for this mechanism of a reaction could be, or is, the reflecting. It reflects the actual reaction process. So you can use the rate, the stoichiometry coefficient in that specific equation to determine the rate, the order, or the stoichiometry coefficient directly becomes the order of reaction. So that first one is if the mechanism, right, of the reaction is given and the reaction is a 1-step reaction and it reflects the entire chemical process. Now, these things doesn't usually happen in nature. It is very rare for you to find an equation. Let's say you have an equation, hydrogen plus chlorine gas combining to form hydrochloric gas, right? And this would have become the balance equation of the reaction. Now, if I told you to determine the rate law expression, okay, let's go. And I tell you to determine the rate of this reaction, and this is a one-step reaction, and this equation reflects the entire chemical process of this specific reaction, then you could go ahead and tell me that the one over here and then the one over here are the orders of the reaction. But if I did not specify these specific conditions, it does not. And then also this reaction over here, the reason why I said this barely occurs in nature is that this reaction over here is not a one-step reaction. First of all, you have these hydrogen bonds over here, hydrogen bonded to hydrogen, chlorine bonded to chlorine, and you're trying to form 2 hydrogen chloride, right? Over here. Now, for this hydrogen to bond to this chlorine, right, this bond between this hydrogen will first have to weaken for you to form some type of bond, and this one would also have to weaken for you to form this type of bond. So you are going to have some type of an intermediate over here that would give you H still bonded to its H but a weakened bond, and then an H bonded to Cl, a weakened bond, and an H bonded to Cl, weakened bond, and a Cl will be bonded to HCl with another weak bond. The bonds have been weakened, right? So that is why I have to only specify these conditions for you to be able to know that that is just the rate order. Now this brings us to our second condition where this rule might still not hold, is if the rate determining step of the reaction is given. Now the rate determining step of the reaction is what? The slowest step of the reaction. And if the rate determining step of the reaction is given, then you could balance out the equation of the rate determining step and find the stoichiometric coefficients, and those would be your magnitude of orders or your orders in the reaction. And even that, it becomes a little bit gimmicky. The reason why it becomes a little bit gimmicky is that there are some times where even the rate determining steps forms intermediate, like this. If the rate determining step has an intermediate, like let's do an example. If we have over here A2 plus B combining to form over here, let me see, A plus B2 combining to form A2B here, right? Let's say it like this. Now, for this reaction to occur, there might be an intermediate step, right? Where the A plus B2, let's say this is a step 1, A plus B2 combine to form A plus B, right? And then an intermediate step where this over here, the intermediate product becomes a reactant over here, and then it will react, this A to B would react with another B2 over here to go and then form H2A 2B over here, right? Now this intermediate that has been given over here, it was a product over here, it has become a reactant over here. If the rate determining step, so this would be the slow and this would be the rate determining step, this would be a very fast reaction, so you use the slow reaction to determine the rate determining step. If it doesn't form intermediate, then you can balance out this equation and use the stoichiometric coefficient. But if it forms an intermediate, then you have to use the law of mass action, which is equilibrium, to determine the concentration of this intermediate, and use that concentration of the intermediate, plug it back into the rate expression over here, and then find your rate constant or your rate orders. So you see how that is. In all this, in the ballpark of all this, what I'm trying to say is that, and I know it's very rare that you're going to see an equation on the MCAT that the actual equation represents you can use the stoichiometry coefficient from the actual equation to become your rate order. So that is number one way where students really mistaken the rate order. It's never that easy, but it is easy. Okay, now the second one is that the law of mass action. Now from here, our next topic is chemical equilibrium, where we will discuss the law of mass action. But one, the law of mass action. Law of mass action, which is the equilibrium equation, the equilibrium law. Let me just spell it all out. The equilibrium expression is never the rate law expression. Now, when we get to the equilibrium expression, you will get to know that they are very, very similar. See, when we was considering like a generic reaction like this, an equilibrium expression of this is going to be like the HCl over here, right, by its stoichiometric coefficient or something divided by the H and then 2 and then the Cl2, and the rate for this expression is also equals to the rate, which is equals to K, right, per either the reactants or the product. So if I'm doing it per the product, it's going to be per the reactant, it's going to be H2Cl2X and then Y, right? So this expression is never this, though they might look similar because they all have concentrations and stuff like that. Or if it is gas, then they will have the partial pressures, but if they are similar, they are not the same. So do not mistaken the equilibrium for the rate law. And then the second one is that this was the second. The third one is that K over here, the rate law K over here, is constant to specific conditions, right? Is constant to specific conditions. So you could say K is not even a constant at all. For example, let's still use this equation over here to say that K is not constant at all, but it is constant for constant conditions. If I have two hydrogen gas combined on chlorine gas to form hydrochloric gas over here, now if I do this under like a partial pressure of say 2 atmospheres and then a temperature of 200 and maybe 80 degrees Celsius or Fahrenheit, let me go Fahrenheit over here, Kelvin is fine. If I do it under these conditions, right, under the pressure of this, and then in the volume of let's say 5 decimeter cube of volume, then the K for this equation, which is the rate constant K for this equation, it is only specific to these conditions. Now if I change the conditions that I'm doing it at now at a 1 atmosphere, K will change. If I do it at another condition, even if I have 2 atmosphere and I change the temperature to like let's say 180 degrees, K would also change. If I change the volume, K would change. So K is determined if the conditions, they are just specific conditions that will determine K. Now if you keep that condition specific, if you conduct the experiment here on Earth and keep these conditions, and we go to the moon to conduct that same experiment but keep these same conditions, K would be the same. But if we conduct the experiment here on Earth and we even stay here on Earth and switch one of these conditions, K would change. So K is not very constant, as in some constants like speed of light, pi, Euler's number. K is not none of those things. K adapts, it changes as the conditions also changes. Now the last but not the least, is that the principles of equilibrium only applies when equilibrium has been attained. Now it might be like, isn't that like a snake eating itself, that the thing is only blue if I see it's blue? Sure, you are right. But the only reason why we say the principles of equilibrium applies only if equilibrium is attained is that when we are measuring rates, we try to do it at the beginning of the experiment so that we minimize errors, because as soon as the experiment starts, the reactants starts eating each other, right? So that would be why it is we only apply the equilibrium when the reaction is over and equilibrium has attained. Now, when the equilibrium has attained, that not necessarily means the reaction is over. It's just that the rate at which I am producing product is equal to the rate at which those products are also fighting with themselves to produce the reactants. So you now have a dynamic balance. If I increase more reactants, I form more products. If I increase more products, I form more reactants. That is the only conditions where you can apply the equilibrium conditions or the equilibrium laws and its, or other shenanigans. If it doesn't say the experiment has attained equilibrium, the equilibrium equations and expressions can't hold. They don't hold. But you can measure rate at any point in the reaction. It doesn't have to be that equilibrium has to be attained before you can measure rates. So these are the 4 mistakes that students usually tend to make when they are calculating rate law. Now, I'm not going to spend time to make an example, work example over here. I'll do that on my TikTok channel. I'll leave the link over here under this video. I'm just going to go and discuss how or some certain types of rate laws that you might encounter. So, or let's say the order of reactions that you might encounter. So, when we talk about order of reactions, we are also talking about the unit of the rate. We are talking about the magnitudes in which the reactants are combining to form its product. When we talk about, so at the first, the zero order reaction. The zero order reaction is when the overall reaction is zero, or the reaction of the rate of each of the reactants are just 1. Now, after saying that, I could say that I could go ahead and be like, the zero order reaction will give me something like A0, B0 over here. The reason why it gives me A0, B0 is that any number to the power of 0 is 1. And the overall order of reaction is going to be 0 plus 0, which will give me zeroth order, the zeroth order reaction, right? So what we are saying over here is that it doesn't matter the concentration of A or the concentration of B. The magnitudes of which they do combine with each other is still in the zeros, right? So if I have like a product forming from this reaction, that product automatically is going to have the same, like C to the power of 0 if there is a product over here. And by so doing, the unit for this rate order is going to be m per second. Now the m is not meters, it's molarity, meaning mole per decimeter cube per second, but we summarize the mole per decimeter cube called molarity as m over there. The reason why it becomes m is that you measure the concentration of this over here. So if you are supposed to find just A, you are going to measure the concentration of A like this, right, to the powers of 0. So the change in concentration all over the change in the time t, and concentration is measured in mole per dm cube over here divided by the second. So all these mole per dm cube is the m over here. So that is why we have these rates to be big M per second. Now the first order of reaction. Where is my tester? If I'm supposed to plot a graph of concentration against time in the zeroth order reaction, I have this conc versus time t. I'm going to have a graph that looks like this, and this graph is going to have a negative slope. Now the slope, which is negative, is going to be the rate constant k, but this time it's going to be negative k over here, so that the negative will cancel the negative, and at the end I'm gonna have a positive k. Comprende. The first order of reaction over here gives me, when I have it like this, is equals to KA1 over here. Now this is the first order of reaction. We find it has a unit of let me see the unit. It has a unit per second, or second minus. Now the first order of reactions are usually radioactive reactions, where you have one product decaying, and it is decaying over time, meaning its mass is reducing or its concentration is reducing. And since it's decaying, it brings the question of, when you are plotting the graph of the concentration against time, you could plot the actual concentration over here against time t over here, and you're gonna have a curved graph over here. But if you plot the logarithmic graph, which is in the concentration of A against the change in time t, then you're gonna have a line that also descend down here, and the slope is still going to be the k, which is the rate constant, and it's going to be negative k, so the slope is going to be that negative k. And the second order of reaction is also given to us by like that. The first the zeroth order was this 0 0. The first order was either K1 B 0, or the other way around, KA 0 B 1. So in effect, if you add these orders, they should give you the order, the either 0, 1, or 2. So if you add 1 and 1, you should get 2. If you add 0 and 1, you should get 1. Those are how they work. And then the unit for this one, the second order, is per molarity per second. Now if you plot a graph of it too, you're gonna have a descending slope where they are similar to the ones that we've already did. And then the higher order reactions. Now the higher order reactions over here, I'm gonna put this This is because it is very rare. The higher order reactions means we have 3 reactants combining to form some amount of product. Now mathematically, it is very rare for 3 bodies to collide simultaneously with enough energy to overcome the activation energy to either form products. So if you run through the universe and you find a higher order reaction, let science know. You might not that they don't exist, they do exist, but you might gain a recognition for that. And the mixed order reaction over here is where you have the reactions, the order of reactions as fractions. So you could be like K A 1/3, and then B 1/2. Like you have fractions as the order of reactions, right? Meaning the magnitude combined in some type of fractionalities to form the products, right? So that would mark the end of our chemical kinetics, the equilibrium. And from now on, we can go solve more work examples about it, so that we do remember. Follow us on TikTok, where we solve a lot of work examples. Thank you. Peace out.